So possible solutions to AGI. Many companies are building this, I told you, and they're pushing as much money as they can to make this happen. And Google is drawing everything they can to make this infrastructure. All right, so the current models they're trying to test out now for AGI is one-shot learning. You can't send in significant amount of data. It's just not going to work. Like I said, you took 1 day to maybe a couple of months to build out one learning system. We refresh almost every night. So how can we have a system that takes a month or a year to learn? So we need to have a one-shot learning where it kind of, after seeing 1 or 2 examples, it kind of figured out, okay, I know what that means. Versus I need to see a million examples to kind of say, oh, I see how that works. It needs to have one-shot learning, which is something that has been hard to figure out, but they've been working on that. Transfer learning. So transfer learning is a system where it's already been learned already, but I can use it in other domains. The same concept here is a function here. You can use the same function over here and make the connection and make that learn as well. That's what it needs to have. Generative models. So generating responses, generating theories, generating ideas. This is typically very, very intensive. And even if you try to do it now, think of a picture of a fish that has, I don't know, hands and feet. You can do that, right? That's something we can do as humans. But it needs to be able to do this as well. The AGI needs to be able to generate things given different scenarios. And again, I said earlier, GANs, general adversarial networks, are good for this because they can be able to generate things and build those as well. And then strong generalization. It can be able to predict things pretty well, and that's pretty much it. Neuromorphic compute. So now what a lot of companies are doing, like IBM and Intel, and I think NVIDIA might be trying to get on this as well, is create the physical computer to represent how our brains actually work, the whole neural or the neurons in the whole architecture that we're trying to do. They're working on that now. They want to actually, instead of using software continuously, they actually want to use the actual hardware to do it. This is actually a pretty good thing. So they're saying, for example, you have the gates. There's no longer using bit systems. These are actually using transfer of knowledge, and the activation is actually on the physical machine, not in the neural network. It's actually on the machine that activates and say, oh, this is actually something that needs to go across. It'll channel it through to the next neuron, and the whole board is made up of neurons. It's really good. All right, so again, deterministic versus probabilistic. Artificial neural networks are deterministic. And I said that the concept of human neurons are non-deterministic. That means that what we think in one state will happen may not happen again. So we have an efficient artificial network that works perfectly well, but when we actually think about how people think, we're not that way. So you can't build a system to do exactly that. So you can't use artificial neural networks in its current state, its current technology now. We have to figure out a way that will be able to understand how people work. So for example, I said all the different neurotransmitters that are in the brain. You see how they come down, flush down to one neuron to the next? That's not always the same way. Things change. And that can be based on concept of emotion, feelings, different types of chemical reactions that are happening. All that happens in humans that are not happening in artificial neural networks. That creates a whole different non-deterministic system. Okay, so abstraction level. I mentioned before, sensory system, typically neural networks are good for that. Recognition, neural networks are kind of good for that for the most part. Well, it's kind of the same thing. And then as we move our way up, the abstraction level, which is reasoning about things, figuring things out, you get into more of the regression and probabilistic models. All right, so I went over this already, so creating functions. Expand and grow. Okay, embedding. So we talked about this earlier with Word2Vec. We talked about this earlier with the whole graph system. Embedding is important. Embedding is important because you're embedding everything with itself around other things. You make connections with everything. You use an embedding system for this. One of the root parts of programming is embedding. I would spend time learning about this if you're going to get into this field of embedding. Regression versus recognition. So we do 2 main functions. We do recognize and recognition, that's probably most of the time, and then we do regression, which is theorizing on learning something new. And that's part of the reasoning process. Transfer learning, kind of talked about that already. Forget memory. We don't forget anything. I mentioned earlier, we don't forget anything. Actually, everything is stored. And sometimes you may think you lost information or you forget something. It's just what happens is when over time things are reshuffled and reorganized, like I mentioned, what happens is those connections may not have been reformed. So it may still exist. It's just not somewhere you made a connection to, because when you're sleeping, for example, the connection may have been lost because you're reorganizing the abstraction at different levels. So something that's been you've probably done a long time ago, you haven't accessed in such a long time, that might have a connection to something else that you completely forgot about. So that's why you should try to remember things before you go to sleep, or read things before you go to sleep. You have a good job with that. So yeah, turning off working memory while you're sleeping. Our agents need to have time, and this is the weird part that we're getting into. Should we have our AGI agents off network and having to do the same things we do, such as reprocess information at nighttime? Or should we have an AGI unit be able to have a separate system that's on the net, constantly doing all of this, while it's physically able to make changes in the real world? That's kind of a weird scenario they're in right now, but that's a lot of talk on that field. All right, so generating models. This is probably one of the most important parts of AGI. It needs to generate solutions, generate ideas, generate theories, concepts, whatever. It needs to be able to do all of this because it needs to make relationships and predict new ideas. This happens because you need to have some kind of probabilistic ideas of where you're going with it. Let me see. I talked about generative adversarial networks again, but we can actually talk about this real quick. So what happens is you'll have a real image come in, right? And you'll have a discriminator network that will try to determine if this is a real picture or not. So what it does is it takes a generator network as well that will create a fake image and send it through into the discriminator. And what happens is a fake image and a real image using supervised learning will determine which one is real, which one's fake. And what happens is it will determine, oh, this is fake, using convolution neural networks again, and say, oh, this is a fake picture, this is a real picture, fake picture, real picture. And at the end of the system, you'll have two networks, one that can generate really, really real-looking photos to the point where people can fool people online. A lot of times you see these saying, I thought that was a real photo. No, it wasn't. It's been generated. And also a discriminator network that can determine, oh, okay, this is actually a fake photo, this is a real photo. And it does this a lot. And you can do this in any domain. It don't have to be photos. It can be any other things as well. Text. It could be fraud detection systems, whatever. You can use this for that.